Hello Stats class, here is lesson 12.1c, which is officially the last new content lesson before the AP test. So we review, we take a quiz, we review some more, we take an AP test. Crazy! So anyway, where we're at in this chapter is we have done confidence intervals for slope, and that was when we were using the sample slope B to predict the population slope beta. Let's label those. And you had a good review of that in the warm-up, so I'm not going to talk about it anymore right now. But now we are shifting to doing significance tests for the same thing. Which means we're going to be deciding if the slope is 0 or not. And we're not going to experiment with other slopes right now. So we're going to basically be always deciding if the slope is 0. Slope is 0 means there is no relationship between the variables, which kind of sounds like what we did with the chi-squared stuff. Or if the slope is not 0, that means there is a relationship, positive or negative, between those variables. So we're going to use the same example that was in the warm-up, which is the helicopter drop experiment. I'm a little bit sad that we can't do that experiment this year. We're just going to read about other classes doing it. So we're going to do a significance test using the information that we had in the warm-up. And I'm just going to do the full 4 steps and talk about the details as I go. So our null hypothesis and our alternate hypothesis, they're very easy in this chapter, honestly, because it's about beta, the population slope, and it's always going to be equal to 0. Actually, I'm going to say it's usually equal to 0 in real life. In this class, it's always equal to 0. I'll put usually just to be more accurate. And that means that there's no relationship. And beta, we thought in the warm-up, you might remember, we thought that it would make sense that the as the height of the drop increases, then so would the time it takes to get to the ground. So we think this is positive because that's the logical thing. So this is saying there is no relationship between drop height and time it takes to fall time, I guess. And this is saying there's a positive relationship. And just to remind you that beta is the true slope of all possible helicopter drops of the explanatory variable is the time, so that goes first, versus drop height. All right. This sometimes is going to be a not equals or a less than in other problems, so I just wanted to remind you of that. We're going to use alpha is 0.05 as usual. If you're not sure, just use the normal one. So all of that is the same type of stuff we normally have been doing, except in chapter 11 we were writing this all out in words, and now we're back to using symbols again. So symbol is your parameter, equals for the null, and greater than, less than, or not equals for the alternate, and then don't forget to define your parameter. Don't forget to define it. Step 2, what we're learning is called a t-test for slope. It's very comforting to know that it's a t-test because we've done other types of t-tests before. We're not learning a new test statistic or anything like that. This is also sometimes called a linear regression t-test. Or you could just say significance test for slope. That would be fine, although t is a lot shorter to write than significance, right? And then remember, we have the 5 separate 5 separate conditions, and we reviewed those in the warm-up, but I feel like I should write them again just to be sure. So random, yes, we randomly assigned the heights of each drop. I'm going to go in the order that I prefer, which actually any order is fine as long as you get all 5 of them, but I prefer to start with the 3 familiar ones, which is random, normal, independent. And for normal, remember we have to plot the residuals and look to see if the residuals look normal. And we did this in the warm-up, but I just wanted to remember, plot the residual. I just wanted to remind you and have it in the notes also. If you plot a box plot or dot plot or something like that of residuals, you're looking for not too skewed. Or if you do a normal probability plot, which is what I gave you as part of the warm-up, then it needs to be approximately linear. And so that's the one we actually used, and I'll just remind you of that. This picture was given to you in the warm-up, and the normal probability plot looks approximately linear. That is how you tell. You could also look at the histogram. Either one of these would work for checking the normal condition, and the histogram of residuals looks approximately normal. So both of these are fine. So it's a yes. You could put yes if you want to. Independent. Well, we normally check the 10% rule, but we don't have to because it was randomly assigned. So I'm just going to say yes, randomly assigned heights. Or just random assignment is all you need to do for experiments. If it was a sample, we would check the 10% rule. And then remember, in the slope world of slope, we have 2 more that we have to check. We have to check to see if it looks linear, and we have to check to see if we have equal variances. And so for that, we also look at the graphs. The scatter plot of the original data is here, and it looks not curved to me, and the residual plot also does not look curved. And then the spread of these different values looks about the same thickness for each x value. The spread of y's looks like it's about the same. There's no fanning going on in those graphs. So linear, yes, because the scatter plot is not curved. Or you could talk about the residual plot if you want. And then equal variance, yes, because it looks like it's evenly spread. So notice that I'm justifying my answers by writing what I saw in the plots. So I'm saying that from my plot of residuals, it doesn't look too skewed. My normal I'm mentioning which plot I'm looking at and saying it's approximately linear. And I'm saying I'm looking at the scatter plot and it's not curved. So justify by saying which plot you're looking at and what you notice about that plot that makes the condition be met. So all of these are, you have to comment on what you see in the plots in order to justify these 3. And I talked about that before, but I wanted to just remind you because we're wrapping up this chapter and I want to make sure you've got that piece. It's a common mistake for students to just say linear, yes. And so don't just stop there. Say, how do you know it's linear? I know it's because the scatter plot doesn't look curved. Okay, 3 are calculations. Now this part's new because we haven't done a significance test yet, but it looks a lot like what we've done before, which makes me very happy. It's like if you already know all the other stuff, this should be no problem. It's always something about the sample. It's going to be the sample slope minus the hypothetical slope from our hypothesis divided by some kind of standard error. And in this particular chapter, the sample slope is called B. The hypothesis slope is almost always 0, so I'm just going to put 0 there and put a little note saying usually it's 0. I might, during the final review, show you one that's not, just for fun, but I've never seen that on an AP test, so we're just not going to worry about that. On the bottom, standard error is officially called SEB, and we learned the formula for this, but we hardly ever need this formula. I'm just going to say the formula is S over Sx square root of n minus 1, and I spent some time talking about why all these pieces make sense. You don't really need to know the formula because the computer output will give it to you, or if you're doing it on the calculator, you could do a little bit of a workaround. So like the calculator will give you B and T, but it won't give you SEB. So if you're trying to show work, you could like rearrange this formula to find out that SEB is B over T after you do the Lin-Reg t-test. So there's a little workaround if you need it, but most of on the AP test, I can almost guarantee that they will give you computer output. On my quiz, I probably will also give you computer output. So maybe in the homework, you might need to find SEB some other way, but not other than that. So let's look at the numbers for this. So I'm going back to the, this is kind of a little messy because I used it last year. Sorry about that. But the computer output that you saw in the warm-up, you already found A and B, and you already found SEB because you used it to make your confidence interval. I'm going to just use that information, and I'm going to take this B, which is 0.0057, and I'm going to subtract the 0, and I'm going to divide by SEB, which we already found was 0.0002. And if I do that with my calculator, I forgot to bring the calculator over here, I'll do that next. If I do that with my calculator, I get 0.0057 divided by 0.0002, and I get 28.5, which is a little bit rounded. If I want it to be super accurate, I would type some more digits, and I'm going to do that just because I want you to see what happens. And I would divide it by 0.002018, which are the actual numbers off of that computer output. And I want you to notice something interesting. In the computer output, here's my B, here's my SEB, and when I divided them, I got 28.37 when I used all the digits. That's the next number in the table. So the computer output table gives you T. That's kind of nice. They also give you P, which is approximately 0. So I'll calculate that just to be sure, but this is 28. I'm going to use the more accurate one, which is 28.37, and that T value was given to you on the computer output. Amazing. That means you really didn't need to do this except to show work and prove that you know the formula. And then P, again, they give you P. You could also find P by doing TCDF, of course. And it would be the 28.37. By the way, that's a huge T, which is why P is so small. 999, really big number. DF, remember, is n minus 2. And in this particular data set, there were 70 drops, right? I'm looking to make sure. Yeah, n was 70. And so we do n minus 2, which is 68, is the DF. And so because it's so big, that's going to make a difference in our answer, of course. So we're going to go TCDF on the calculator, 28.37, and really big number, and 68. And that ought to be nearly 0 because that's what the computer rounded it to. It's kind of funny to look at it. It's 1.03. Please don't stop there. I still have some people occasionally stopping and saying, oh, the probability is 1.03. Probability can't be bigger than 1. So if you see a number bigger than 1, you need to look over here and make sure you notice that it's times 10 to the negative 39th. Which is 38 zeros and then a 103. It's approximately 0. You can leave it in scientific notation. Please don't write out 38 zeros because that's just too much of a bother. But it's really, really close to 0, which is why the computer output rounded it to approximately 0. Okay. So we can reject. And actually, that's not a big surprise with this context. If the drop height did not make a difference in the time falling, I would really be wondering about the laws of physics, wouldn't you? It's just, what? Conclusion. Let's write our conclusion. Since P is approximately 0 and is way less than 0.05, we reject the null hypothesis that, here's where we need the context. So there's two ways we could write this. We could write it just based on the no relationship idea, or we could talk about the slope. I'm actually going to do it both ways. I'm going to say that there's no relationship. We're rejecting that there's no relationship, which means we conclude there is a relationship. So no relationship between drop height and time. And then we make a conclusion about our alternate hypothesis, which we've done that in other chapters before, and I want to remind you, we said greater than because we thought it would be a positive relationship, and this very, very low p-value is evidence that that is true. We conclude that there's a positive relationship, and I'm going to put that in context by saying we conclude that, this is so obvious, that dropping from a greater height takes longer to fall. To the ground. If you drop it from higher, it takes longer to fall. Oh, wow. Everybody knew that already, but that's just an example of how to do a significance test for that. So the 4 steps should be so familiar to you by now. State, plan, do, conclude. Almost the same as what we've done in other chapters, except now we're using slope, and we'll most likely be given these numbers in computer output, and you would write this for me to prove that you know the formula. That is the only reason you would need to write this. If you're using the calculator shortcut, then it would not give you the SEB number, and so you could get it by doing B over T and fill it in to show your work. It would give you these 2 numbers, and that's a little bit more bother, but it's not so bad. So there is your official 4-step significance test, and that is it for these notes. The next lesson is review, and we'll make a chart and all of that in the next lesson.